Okay, let's get started in this next session, which is titled Deep Learning and Related Topics. So, could capture all sorts of evils. I just wanted to set the stage a little bit by going into some concepts that I've worked on with Dr. David Stark, who spoke yesterday. He's at Mount Sinai. Together, we decided it was important to come up with a paradigm that represents an opportunity space for developing, I should stand in this circle, for developing methodologies, models, systems that can be deployed in increasingly more ubiquitous fashions external to the clinical settings in ways that enable data capture at a pace and at a quality that's consistent with what we need to do in terms of model development that are both shallow and deep types of models. So this opportunity space includes three axes: a signal axis, a sensor axis, and a platform axis. And in general, we want to kind of move in a positive direction along each of these axes, although it's not always possible. For example, moving from along the signal axis, moving from behavioral measurements that are inherently subjective to more objective physiological measurements. Moving from sensors that are rare, like an MRI machine, to sensors that are increasingly common and ubiquitous. That would be in the form of smart devices, wearables, smartphones, and so forth. And engaging our participants, the constituents that we wish to address with respect to healthcare issues, in increasingly more passive data collection fashions. So moving from activity where you're doing, let's say, keystroke dynamics or doing direct engagement, clinician to subject, questionnaire, to passive data collection, utilizing the Internet of Things. And of course, all of these concepts enable us to think about what are the opportunities in terms of tool development, model development, and commercial industry development that can begin to address some of the major public health concerns that we have today. And some of those things will enable us to do better data collection. Some of these things will enable us to engage our constituents much more efficiently, flatten the earth, enable global reach as opposed to local reach, enable cost economics to scale, not just within the country, but out to other countries, and things like that. So I like to put my thinking into this context and plot my sort of next endeavors into this opportunity space in order to be able to develop models that are practical and can be deployed in ways that reach the global population needs that we try to address. One of the companies that I've worked on is... Say hi! Say hi! Can you tell me your name? And it fits within that opportunity space, of course, somewhere in the middle. Basically has some active component to it, but also works on ubiquitous devices, smartphones. Yesterday, I gave a short talk, and I asked the audience to pick out the kids with autism in this slide deck, and I echoed in that particular context that this is meant to provide, this slide is meant to describe the situation that we generally know to be true, which is that doctors who work with children who ultimately get diagnosed with autism have the empirical intuition to diagnose them very quickly. They have their perceptons necessary to see very quickly within this six-slide, this scenario of 6 children, which of the 3 kids have autism. And it doesn't require lots of measurements. It doesn't require a lot of time. It doesn't require a great deal of model complexity. And yet, they don't act on this intuition, in part because they don't have the quantitative tools necessary to do so. And so Cognoa is attempting to try to build some of those quantitative solutions and enable an answer to be delivered to the doctor to assist the doctor in making a very quick decision that's robust. But it's important to note that within that opportunity space, deep learning can be, there are opportunities for deep learning, and there are also some areas where we have to do a better job at data collection to provide examples so that we can ultimately train a deep learning model to work on complex videos like that, where we're looking not just at gross characteristics that are easily discernible as with edge detection and other things like that, but subtle characteristics, social characteristics that are much more challenging. So Cognoa in part works towards that goal of being able to have automatic extraction of critical social features from short videos to be able to render an automatic diagnosis as opposed to a human-assisted diagnosis. But in order to get there, we have to label. And so naturally, we've created a system to make that labeling possible. And we've made it such that we can do labeling very rapidly within the context of a short video, utilizing multiple raters simultaneously to get inter-rater reliability, multiple labels per social interaction or social scenario that's important for diagnosis, all to render the information that provides the doctor the intuition to act, provides the doctor the quantitative information to act quickly on their intuition while building a label database that we can utilize in the future, hopefully in the very near future, to develop a deep learning method that will replace some of the semi-automatic human-in-the-loop components of this system that exists today. So I'll just keep moving. Similarly, this platform that I also described briefly yesterday of delivering wearable therapy to children, teaching children with autism how to understand emotion and faces, a fundamental deficit that must be rescued in these children. Here we employ deep learning, but we also employ a method of data capture that enables us to adapt the model over time. So what I'm getting at is that deep learning has a tremendous amount of promise, but for situations like this where we're trying to do interventional therapy or identification of subtle social features in an automatic fashion that scales to a global population and that fits on the further edges of the sensor, platform, and signals axes of this opportunity space, we have to create a mechanism to deliver solutions while capturing robust labeled information that provide examples to the deep learning algorithms we want to train. And that's exactly what this does. And I'll give you one final example of what I think we can do in this endeavor to build better models. And that is capitalize on the opportunities that games can provide. So has anyone played Heads Up before? Do you know this charades game that's on your phone, promoted by Ellen DeGeneres? Anyways, yeah, so some people have played it. That's a really cool game because you can actually show images. You know, we play this commonly with my children, and they act out these emotions, or they act out what's being displayed on the screen. While that's happening, a video is being recorded. We've decided to capitalize on that same concept to create a charades-like game to get egocentric video of an individual's face, so that we can automatically extract features from that video. So for instance, we can apply a convolutional neural net that is trained to recognize the face and trained to recognize emotions to the video that's captured when the child is acting this particular emotion. And the moment in time when this surprise face corresponds with the solution, the outcome from that classification system, is the exact moment in time where we have 2-point correspondence. In other words, a convergence on labeling that's automatic. We have an automatic game solution and an automatic convolutional neural net that together correspond and provide us with robust indication that the child's face is indicative of happy, angry, and others. And so this provides us with an opportunity to build a very large label data set on which we can build machine learning models, deep learning models. Today's session is incredibly exciting. I'm humbled to be up here with these luminaries in their respective fields. And so what you're about to hear are some of the things, maybe touching upon what I just described, including some of the things that are, I think, important for deep learning in its application in medicine, including the ability to have a robust metric for evaluation of AI, limitations of deep learning, and how to work with locally interpretable model agnostic explanations. And then I think this is somewhat related to my topic, talking a little bit about 21st century patient care and empowering patients. And finally, we'll close with the interplay between data scientists and physicians to create meaningful solutions. So let's get started.
Thank you. So first of all, I want to thank Anthony for organizing this excellent event. So today, while I'm actually originally prepared this talk only for deep learning, but I realized that there are more critical issues beyond deep learning. So that's why let me actually quickly dive into what exactly the issue we're facing right now in the AI in medicine. So right now, we all know that in the 21st century right now, we're under the paradigm shift from reactive, reverse engineer to fix a sick body, from sick care to the health care, where we actually want to take a proactive care to actually do forward engineer. And in this whole process, we all know that right now, individual population, we want to go for predictive personalized health. We are undergoing tremendous technology revolution, such as sensor technology, imaging technology, robotic technology. And then we all know that all this, people call it AI, but we used to also have a discipline for that, biomedical health informatics. It's actually play a role of accelerator, enabler, and hub. Why? I'm actually putting a real title to be translating AI for medicine and health. As I said, medicine is current practice, healthcare is the ultimate. The reason is, if you look back about since computer was invented, since 1950s, I think Jeremy or someone also mentioned that already, there has already been push to use computer-aided diagnosis to help us. And then in 1980s, when I started my career in AI, it was a big wave to push AI, a big promise. Why? This is the third wave. Why? For more than half a century, we're not there yet. Largely because we're lacking the fundamental, many good, successful stories. So that's the reason why it's very critical while everyone is talking about the AI, instead of avoiding AI to become another hype in this third wave, we really need to think about how we translate AI to have a successful story, to save millions and billions of people's life. So that's why if we actually come into this, this is what I actually suggest. Originally, as I said, because we're talking about deep learning, I do want to point it out that these are the 5 things are really critical when we're actually talking about translating deep learning and AI into medicine and health. So number 1, data quality matters. Garbage in, garbage out. That's actually, everyone knows it. But right now, we're talking about the reality. In reality, we will never get a perfect, clean, accurate data. So that's why we have many, many challenges while we're thinking about AI. How do we design experiment? Number 1. Right now, number 2, if we're talking about deep learning, we need a large amount of data. Then when we need a large amount of data, how do we deal with these silos when data being collected? They're not standardized in the same format. And then, number 3, while we're dealing with the data, if we want to normalize the data from different sources of collection or different devices for collection, what if we actually should be dealing with rare diseases, looking for the special outlier? It makes sense. We don't want to get rid of those. All those things introducing a dimensionality, that's called variety, or the issue. Deep learning can help us on that. Second one, in fact, I had a type O here. I mean that algorithm robustness matters because reproducibility in the clinical practice matters. So in that regard, it's very important for that. Third one, integration matters, and the interpretability matters. And last one, human matters, people matters. I'm just going to, these are my key messages for deep learning. It can bring benefit for that. At the same time, it has huge challenges. I will summarize at the end. But for the rest of the slides, I'm just actually going to explain a little bit more about each of this. Some of you probably were in the workshop. I already mentioned that. If you're talking about top 3 causes of death in the US, everyone immediately knows what are the top 2? Cancer and the cardiovascular. But what exactly the third cause of death in the US? Believe it or not, is actually the medical errors. Medical errors involve multiple steps, including the clinical workflow, data collection, everything. But really, large amount of those contributing to the data processing step. If we're actually looking at Anthony said this morning, we also need to care about small data. But let's actually also be real. In fact, we are in the middle of data tsunami right now. We're looking at, by 2030, we're going to get yottabytes of data. I did a small quiz on the workshop day, asked how many zeros for yotta. I don't see any hands raised. I can tell you we're looking at, in the US alone, we're talking about 24 zeros after 1. That's actually the data we're talking about from omic, molecular data, imaging data, not only the medical data, but the behavioral imaging data, as well as a huge amount of sensor data. So that's why when we're actually talking about what I just said, if you have data collect from different sources, let's actually take a step back, just talking about electronic medical record alone in US, not even talk about the entire world. We have a Cerner, we have Epic, they don't use the same format. So how do you deal with that? There's a new standard coming out called FHIR, Fast Health Informatics Resource. That's actually the one to help us with deal with information exchange. But still, we need to develop more standard related to ontology for language description, as well as the data, quantitative data standard. And so that's the reason why deep learning can help us in terms of it provides some robustness beyond the traditional cellular learner can provide to us. And now, Anthony already showed a pyramid. I'm actually repeating that pyramid, except I want to highlight the important thing here. When we're actually talking from data extract feature, we actually go into the knowledge that's very critical related to medical decision making, and then to action, decision and final action. In this whole process, it's actually not a linear model. It's actually like a feedback loop. But why I put this particular slide here? Because I was being challenged already by people that is actually AI going to replace the people. What I say is it's impossible. And actually, the reason is, even Anthony gave an example that robot can pass the exam, but in reality, in the entire care for human, there are many steps. Human cannot be excluded in the process. Data collection, data decision, making, deal with the cases you don't have in your knowledge base, the inference ability. The final important reason is the step of human touch. Nothing can actually be more beneficial to very ill patients than the human interaction and the human touch. And also, of course, for advancing the science, as Anthony mentioned, the human interaction is also very critical. Now, let's talking about the pipeline matters. FDA is running this challenge. Remember I was talking about the robustness of algorithm? This is a simple medical genomic. They're trying to develop a guideline for proving the new medical genomic. Looking at the next generation sequencing alone, there are more than 200,000 possible pipelines in analyzing it. Does the pipeline matters? Can algorithm be more robust? Actually, believe it or not, this is coming from this FDA study here. We actually find out that already proven past the clinical trial using the different pipeline. Unfortunately, algorithm pipeline matters. You use a different pipeline. What you used to be able to make a right clinical diagnosis right now is completely wrong in terms of prognosis. So that's the reason why deep learning can come in and play a role. If you want to know more about what deep learning in terms of robustness, on the workshop slides, you would be able to find. I don't have time for that, but I want to tell you that one of the benefits for deep learning is actually it's provided inherited robustness there. And second one is integration matters. Deep learning can also do that. This is a simple case of starting California collected for Alzheimer's disease patient, differentiate a healthy population, Alzheimer, mild cognitive impairment, and then the data being collected with the imaging, like MRI, PET imaging, as well as the electronic health record and genomic data. And so by doing these deep learning, as I said, deep learning has some embedded robustness there. And then it's already proven that integrated analysis is better in individual analysis, number one. Number two, for shallow model versus a deep model provides better results. So now, however, when I talk about how good deep learning is, what's the fundamental challenge of deep learning? Until now, I think yesterday we have an imaging group talking about deep learning. Everyone starts getting excited. But I also want to share with you, until today, even in the highest level, when we actually, in the panel, review many this kind of study and the proposals in a federal government review panel, only deep learning now show consistent performance in image analysis. For electronic health record, for the genomic, like proteomic, metabolomic, unfortunately, until today, it's not stable. Sometimes it works, sometimes it doesn't work. What's the reason? We can debate about that during the discussion phase. But what I want to say, though, is with all this issue, I want to really share with you. This is actually, we come out from this national strategic discussion, a committee, discussing what are the challenges we're facing in AI, in deep learning, especially translating it for the practice. So these are the 5 of those. The first one is data integration, how to deal with the existing reality of not quality data. So as I already said, standardization, bias in collection, how do we develop a new AI model to be able to deal with that, such as deep learning. Second one, integration. How do we utilize it? Third one, I think also Anthony mentioned this morning already, is actually the causality plus the correlation is very critical, because that's a resemblance how a human being is thinking. And next one is this real-time decision making. So adaptive learning, that's where I was talking about. If you are training your model, you are actually having new population come in, new ethnic group come in. Unfortunately, a lot of time models fail. So you have to be able to do adaptive, like changing of your model. And the last one, metric and validation. This is where I said human matters. We have to first be able to interpret our model. And this is what I think Crystal also mentioned about the black box. Black box, unfortunately, sometimes, fundamentally, the damage it does is actually impact the trust of like human. Who is liable for the wrong diagnosis? As I already showed you early on, if you pick up the wrong algorithm, you have a wrong diagnosis. So that's the reason why this is becoming one of the 5 grand challenges and at the same time opportunities for AI community. So the last one is there's a big debate about should a physician learn data science or should a data scientist learn medicine. I actually can tell you a very mind-boggling statistics. I already told you that 3 waves in AI. Unfortunately, less than this finger percentage, right, 5% of the system ever being put in use in practice. That's why we lack a successful story. So among which, what are the fundamental barrier? That's the human part. Remember I was talking about the pipeline? The most critical one is knowledge modeling. People like me, I'm a computational trained. I have been trying my best to develop a system, but that doesn't capture exactly the clinical, medical inference the physician can have. For that regard, we have to bring more physicians into the field. And with that, I'm just quickly made one comment because I heard this debate already. As a practitioner, how do you get involved in AI? 4 courses I always recommend. Actually, taking a MOOC, open a source course is good enough for you to understand. 1, statistics, understand the basics for metric. Number 2, pattern recognition, because reduction approach doesn't help you to get the natural principle, what it is, but help you to understand how you categorize your knowledge. And number 3, intro to programming, because the sequential programming to model the rule is very different from human mind. A nanosecond, you make a parallel decision. So you want to be able to understand that. The last one, but not the least one, is very critical, visualization, because that's for interpretation, for human usability. Thank you.
Thank you, May. Michael.
Good morning. I'm Michael Fahey. I'm an Associate Dean and CTO of the Schmidt College of Science and Technology at Chapman University. And Anthony's asked me to talk about limitations of deep learning in medicine. I'm kind of drifting about this idea. Perhaps I'm going to be talking more about perceived limitations because I'm going to see if we can find some solutions to some of these issues. So you all know what deep learning is all about now, neural networks and deep learning having multiple hidden layers. I think that a lot of the problems that we have with deep learning right now is the lack of theoretical foundation for what is going on. Last year I showed this slide from DARPA about kind of a capriciously named project they have, FunLAL, the fundamental limits of learning, in which they try to find some of these answer some foundational questions, like what's the number of examples needed for a deep learning system? What happens when you have bad data? What's the efficiency of the algorithm? So these are the kinds of questions that we're used to being able to answer for traditional statistical approaches, and we don't really have answers yet for deep learning and machine learning. So abandoning the theoretical foundational approach, a lot of people have been successful with empirical approaches. The big question problem that everybody's been talking about is this black box idea. Deep learning is a black box, and the result of that is that we have trust issues. How can we trust that the answers are correct if we don't know how the system works? But there's other problems as well. How can we predict the behavior? How can we predict how it's going to react in a new situation? What can we do to improve it? If we don't know how it works, it makes it difficult to make an attempt to improve the model. So what I'm going to be presenting today is an empirical approach by a team from University of Washington. This is the LIME method, locally interpretable model agnostic explanations. So Dr. Samir Singh gave a presentation at our local Orange County ACM chapter meeting a couple of months ago. And this is an attempt to answer or address some of these questions. So some of this was mentioned yesterday. I was kind of hoping that nobody would say anything about interpretability of black box models, but it was addressed by, who was it? Matthew Komorowski showed in one of his slides a list of the most commonly occurring attributes or features in his model. And one of the panelists last night at the open forum said there's no such thing as a black box because we can figure out what the deep learning model is actually doing by looking at features. And that's what this is about. So let's look at a standard deep learning application, image recognition. We've seen the cat and dog one. This is maybe a little bit more risk involved because you're trying to adopt a pet and you want to decide whether it's a wolf or a husky. Still, you got two animals there, and you train a model by showing it a whole bunch of images that you know are what the outcome is, and then you give it some new images and you let it make decisions for you. So in this one, it decides it's a wolf. This one, it decides it's a husky. So the question is whether you're going to adopt this animal or not as a pet. So we'll show you the results of some of the classifications, and you can see that the model is really pretty accurate. It's almost always right. It just made one mistake. Well, that one mistake could be pretty significant. But by looking at this slide and these outcomes, can you decide what is it that the model is actually doing? How did it decide by looking at these images which ones were nice, friendly pets and which one were predatory animals? What is it actually doing? How is it operating? Well, that's what the LIME approach is designed to address. So how does LIME work? It provides these explanations. And an explanation is achieved by taking a specific prediction of a classifier and then looking at subsets of the data that classifier was given. In this case, subregions of the image. Doing this thousands and thousands of times and seeing which sections of the image showed up most frequently in its results. So you find the predictions of the classifier on a subset that agreed with the prediction of the classifier on the whole image, and you say that the classifier is looking at that subset of the image. So by doing this thousands of times, we can decide which portions of the data the classifier is paying attention to. This could be done for clinical records or images. It really doesn't matter what kind of data it is. And Matthew's example yesterday showed this kind of thing for clinical records. So let's look again at the same set of images now with the explanations. Circled are the ones in which the deep learning model predicted a wolf. You might be a little bit surprised by looking at this, but can you now take a guess as to what the model is actually doing? How is it coming up with its prediction? All right, time's up. What we've really got here is a snow detector. We think the model is doing one thing, but it's actually doing something else. It's looking for and detecting the images that have snow, and it's saying, well, those are the images that have a wolf. So this is an artifact of the data that has absolutely nothing to do with what the model is supposed to be trying to find for us. But it turns out that by looking at this explanation, we can see that that's what's really going on. So I don't know what your opinion of the model was before in terms of whether or not you would trust it, but I'll bet it's changed when you've looked at this explanation. So this explanation might not give you the greatest confidence in saying that a model is absolutely correct, but it will help you to abandon models that don't really work that well. So this method, and this has become a pretty hot topic in data science. The whole idea of interpretability of models and explanations for models. There's a lot of work being done on this right now. This LIME is the one example I'm most familiar with because we had a presentation from Dr. Singh. But what do these kinds of quantitative explanations do for us? Well, they help us understand the behavior. They help us make a decision as to whether the model is trustworthy or not. They help us understand a little bit better what the classifier is actually doing. So it's really shedding some light into that black box. We're opening up the box, we're looking inside, and we're seeing something about how it actually operates. It helps us to compare two different models. So if you saw another model that was just as accurate, but in the explanation it was actually looking at the animal as opposed to looking at the snow, you might have more confidence in that one. It might help you improve the existing model. In this case, you might go back to the drawing board and say, hey, look, at the training data that I gave, it was flawed because all the pictures of wolves had snow around them. I need to give it it's a different kind of data to train on if it's going to be effective. And it helps us predict how the deep learning model is going to behave. In this particular one, if you showed it a picture of a husky surrounded by snow, you're going to say it's going to be wrong on that one. It's going to say that it's a wolf based on the explanations that we've seen. So if you want to learn more about LIME, there's the GitHub repo. You can download the code. You can apply it to your own models. You can contact Dr. Singh at his website there. These slides will be, of course, given to you as part of the package. And one last thing in terms of collaboration between data scientists and physicians, this was a talk that was given at a local ACM chapter meeting, and we have an Orange County, that's the website of the Orange County ACM, and the full set of slides from Dr. Singh's presentation and a YouTube video are available on the ACM website, and this will be given to you as part of the presentation here. And there's other good talks that you can participate in at your local ACM chapter, so that's my plug for the ACM. Thank you very much, and I'll pass it on to the next speaker.
All right, let's take a little different journey here. When I was developing this presentation and all the discussion which has been going on for the last 2 days, we are talking about healthcare. Well, before we go there, my name is Gora Dada, and thank you, Dr. Wang, for giving a plug for HL7, so I don't have to do much as an HL7 ambassador. So let's look at deep learning and EHR, and let's see what the impact is on for the 21st century healthcare, which I said, no, not really healthcare, patient care, the empowered patient. Now, why did I do that? Just take out your phone, do a quick Google on healthcare, and you'll come up with this definition where it very clearly says, where I've underlined, delivered by the health professional. Try to do the same thing for patient care. Tell me what you find. Now, if some of you agree that, or may suggest that, no, it's not really patient care, it's consumer care, well, if you Google consumer care, then that's a different story. But staying with patient care, and the argument which I'm making is we are now living in a world which is changing very rapidly, and it's quite different what it was in the 20th century. And why do I say that? Because the 20th century model is where the caregiver is providing care to the care receiver. And I want us to flip it on its head and move it to the world where the care receiver is obtaining the care from the caregiver. In fact, when I was writing this slide, I actually first wrote demands. And then I said, no, let's start with obtains. The point which I'm making here is we have to bring in a disruption in the way we deliver access and deliver care to our patients. This is how all the disruptive technologies have evolved. Let's take the most recent one in terms of Uber. Before Uber came into existence, in terms of a delivery service, the way we were looking at improving the service of providing shared cab was, okay, how can we have a better cab share service? nobody was really thinking of the model which Uber has done. And if you go back, we're starting with whether it's Amazon, whether it is Facebook, whether it is Google, any of the disruptive technology they have started with, it was quite different than what it was before. That's why it's called disruptive technology. Even in healthcare, this is what I'm saying, that we need to disrupt the way we provide care, way we demand care, and why. So let's, and I'm stealing from my own presentation 2 days ago on the workshop, so I apologize for those who may have attended that. But here's a little bit of a 2 minutes overview of what I presented there. This is what I talk about patient care in the 21st century. You just have to look at your kids or your grandkids, what I call the iPad generation. Take any 2-year-old child anywhere in the world, may not know how to speak his or her mother tongue, but they know damn well how to play with their dad and mom's cell phone. And every dad and mom tries to stop that, and they fail. Or you watch the kid watch up to the TV in the living room and try to swipe the TV, because that's how they are used to movement. So the point I'm making is this is a very different generation, and so they are being born to think digitally. They are being born to think through interaction with devices. Therefore, their expectation is very different. In my day job, I work with providers, and I tell my providers that do not expect your future patients to call up and make an appointment, change an appointment. No, they're going to go to their iPads or whatever device of choice. And if you're not there, they're not going to call you. And you can see that today when you have 2 kids, teenagers or otherwise younger ones, sitting on the table. They don't talk. They Snapchat each other. And the impact of what we are seeing in terms of social media, concept of privacy, it's quite different. Blurring of line. What our concept of privacy is, what the concept of the current generation is very different. So again, we have to look at it in a different manner, how we deliver service, what is secure, what is not secure, what is private, what is not private. Sorry. This is the one I'm sure all of us face. That are we there yet now? I want that information now. This is the way I say, and I'm sure my wife will kill me for this again. It's like we have no longer a teenage son. He's in college. And if he has not replied to mom's text in 30 seconds, after 2 minutes she's panicking. Something's gone wrong because she wanted that information now. She wants that feedback now. So we are living in the world, we want that information as consumer. And that's why we want, and we are now taking charge of our healthcare. So this is where the demand part of is coming in. So all our service delivery needs to keep that in mind. The new generation is is demanding information in a very different way. We are no longer living in the world where we quietly went to the physician told us what to do, and we walked away. Today, to quote my primary care physician, a good buddy of mine, he said, Gaurav, thanks to Google, I have to be on top of my game. Before I finish my sentence, my patients have whipped out their phone and they're Googling what I'm telling them. So we are taking charge, all of us. And therefore, we need to recognize that our patients are doing that, and we all are patients. In fact, Anthony, I have a suggestion that for the next generation or the next conference, we need to have patients come in and talk about what their needs and expectations are. What was science fiction? And Crystal, yes, I have grown up with the Star Trek generation, watching all that. And what was science fiction 20, 30 years ago is now a reality. It's given. So it's a very changing world. And therefore, again, I go back to the same thing. How we access information, how we deliver care needs to be very different. And there is a reason why almost all the tech giants of the world today are spending quite a bit of money in space technology. One of my workshop slides really spoke about, okay, let's look at what was there 100 years ago, 1917. There was no commercial flights. And in 2017, look where we are. Similarly, today, there is no commercial space flight. Who knows what will be in 2117? Just keep that in mind. But what that means, which means our health information needs to go across. Today, we don't have a mechanism to do all that. Moving ahead, and that really leads to the next aspect of, Back to Future, what I call longitudinal health record, we are now living longer. Thanks to advances in medicine, we are no longer dying at the age of 55, 60. That's where the retirement age was set then. We now start living at that age and live for the next 30, 40 years. So therefore, we expect, and thanks to the advances is genomics and related sciences, we are expecting our health record to exist beyond 100 years, 150 years, maybe even more than that. But if you look at any of our existing media today, digital media, their lifespan is only 30 to 50 years. So we have a little bit of a challenge there. How do we preserve information? And that really comes to the provenance and preservation of data, which I'm talking about. With all the electronic and digital information coming from all way, we have to be very, very, very sure of the provenance of the data, notwithstanding cybersecurity, and that is really throwing a wrench in the spanner. Just imagine, it's no longer an issue of your health data getting compromised because everything is digital. Think about it. If a bad character or bad actor introduces a bad data, suddenly your health record is showing a disease which you don't have. And think about it, how do you go about changing that? So we have to be careful about the provenance of the data and how do we preserve the data across the lifespan of the data. And remember, the data is coming from all sources, not just one source. You don't just visit one provider. You don't just visit one hospital. And so you know what I'm getting at. These are the emerging areas. There's a lot of discussion going on in terms of HOT, by the way, is healthcare of things. I don't like saying IoT of health, but I say hot stuff is a better acronym. Big data, cloud computing, we are obviously hearing a lot about this, but what we haven't heard much, there's a little bit about it, the augmented reality, virtual reality, and mixed reality. And this is where I'm seeing some awesome opportunities coming around in the healthcare space. We live in a connected world. What is happening in a remote part of China comes around as SARS today. What is happening in some remote part of Africa is Ebola here tomorrow. What is happening in Middle East is Middle East respiratory syndrome tomorrow, which is out here. The point is, it doesn't matter where we are, which part of the world, we live in a connected world. And it is not just healthcare which is impacting our care, it is also the social determinants of health. How we live, what kind of air we breathe, whether we have food, whether we have shelter. These all have to be factored in the care, in the decision making and the learning we are going through. Again, the micropayments. This is something which we are now seeing, the wallets. We are really at the very early stages of trying to understand how we can deliver micropayments through the devices we have. And there are other related parts to having the mobile device being the enabler of service delivery. Take care, cyber health, I talked about a little bit. This is really the cybersecurity aspect of it, blockchain. So I won't be getting into it. The idea of this is just to give you a sense on where we are going with the 21st century, and finally, why this conference is all about, AI, machine learning, deep learning. So the point which I'm making is that in the 21st century, whether you are a quantified self, young and able, looking at all kinds of sensors, and which is giving you all kinds of data, or you're living healthy and want to live beyond the age group you're striving for. Either of the two spectrum, this is what the future is all about for us. So what are the deep learning opportunities in EHR? This is well known. We have in this country at least over 10 years of EHR data. In some other countries, they have a little more advanced than us, but let's look at the US. We already are trying to look how can we apply deep learning to whether we are talking about various kinds of medication lab or regular imaging orders, the vitals data we have diagnostic data. So all this is information we already have. The one which has come about in the last couple of years is a quality measure and the improvement, whether it is a process improvement or whether it's outcome-based improvement. So we are just about scratching the surface on deep learning and the possibilities out here. But these are the emerging opportunities for the 21st century. Patient engagement, it's key and critical. We really haven't done anything out here. The only thing we have done today with the electronic health record is the patient portal. That's really what I call the 20th century idea. It is, I work on a regular basis with clinics and the patients. patients don't use patient portal, period. We have to have a better way of interacting and interfacing with the patients, whether it's a mobile health record or not. We are seeing a proliferation of mobile health apps. Just give you the latest count, we have about 175,000 mobile health apps in the marketplace today. Think about it. Although a very small percentage actually work, but still it's a very large number. Mobile medical devices, IoT devices, these are all really on the rise. Patient-reported outcome has been talked about a little bit, or the patient-generated health data. So what I really liked, the previous session we had, the human-generated data, what Anthony, you had, I think, in one of your slides. That's what we are talking about. We are now in this century where we are generating a lot of data, and this is where I see the opportunities for deep learning, which comes in. And I touch upon the social determinants of health a little bit to just give you a flavor of what are the opportunities there and many more coming in. So I just want to leave you with a thought that 21st century health care is really 21st century patient care, where the patients are empowered, and we have a lot of opportunity in deep learning and machine learning and AI in that space. Thank you.
Hello, everyone. My name is Neil Tenenholtz, and just before I get started, I want to apologize if you get a few coughs here or there. I'm on a bit of a whirlwind tour right now, 3 conferences, 4 cities in 3 weeks. So, yeah. I want to also thank Anthony for organizing this event. A couple weeks ago, I was at RSNA, so that's about 60,000 folks. Last week, I was at NIPS, closer to 8,000, and now finally here, a little bit smaller, more intimate, and I really like that. It's nice to be able to chat with a significant percentage of you. Anyway, so I'm going to be talking about developing clinically relevant solutions for healthcare. And this is just my opinion, so I want to be perfectly clear. Some of you may disagree, and if you do, that's perfectly reasonable. And so before I get started, I think it's a reasonable assumption that you should know where I'm coming from, why I view things the way I do. And so my expertise has spanned pretty widely across the healthcare domain, at least from the engineering side. I'm not a clinician, I am an engineer. And so I've worked on surgical robotics, I've worked in surgical simulation and training, I've worked in hospital logistics, wearables, and now I'm at a group where we're using machine learning on medical imaging. And so while this work has spanned quite a variety of disciplines, I think there's one thing I've learned, and I suspect for the clinicians in the room, it's pretty obvious as well. It's basically that providing anything to a hospital is slow, it's time-consuming, it's burdensome. And this isn't really surprising once you've been in a hospital. You learn it pretty quickly. Sometimes it's frustrating, but it is what it is. It's the environment you're working in. And I think when you're trying to develop solutions for these environments, you need to realize the space you're in and you need to adapt. And so when you're developing these solutions, I think one of the first things you need to address is, what is your target? If in terms of, so I'm going to focus on medical imaging. I think it's probably the most relevant for this audience. And so a lot of folks have talked about, can we replace the radiologist? And so maybe you've seen this article, or this one, or this one. I mean, the list goes on. I could just keep flashing these for 10 minutes and you wouldn't be surprised. Yeah, and I think a lot of folks think that's possible. I'm a bit of a skeptic. And this is from someone who's developing the models, mind you. And so one of the big challenges is, you want to replace the radiologist? How are you going to get these models adopted? You're going to go to the radiologist and say, hey, we're here to take your job. Let's go use these models. Let's go validate them. Good luck. And so maybe there's a few other options you want to pursue, whether it's improving quality of care. And that's great. That's a very noble goal. It's very important. But there's some challenges there as well. Who's going to pay for that improved quality of care? Are you asking the hospital to go at risk? If so, there's going to be some challenges involved. It may be easier in the future as bundled payments become more common, but right now it's not going to be easy. Maybe you're trying to increase revenue for the hospital. It's also a bit challenging. I think healthcare is one of the prime examples of a market where demand is inelastic. When folks are sick, they're sick, and they're going to do whatever they can to remain alive. I mean, there are a few exceptions. Cosmetic surgery, for one, for sure. And also folks like Intuitive, where they developed the Da Vinci and they convinced patients that having your procedure done by a robot is better than the patient, or is better than the clinician. And so folks would go to hospitals and shop hospitals that had these robots. And so you can do it, but it's challenging. And so the easiest solution is probably going to be to decrease costs. And so now it becomes an efficiency play. Can you fit into the workflow? Can you make the clinician more efficient? And I think that's important to keep in mind moving forward because it's going to impact a lot of your decisions. You need to set these metrics early on and figure out how are you going to do this. And so because you're trying to decrease costs, you need to understand the clinical workflow. What environment are you placing yourself in? How are the clinicians going to use your software? And so as an engineer, we like to simplify things. We like to make assumptions. Here's this problem. The radiologists, they read an image, they write a report. Simple, let's just make them better at reading images. Except we're really bad at this. We make really poor assumptions. We don't have the clinical expertise. We haven't sat in the reading room with you typically. This was a comment I think I saw earlier that that the data scientists should round with the MDs. Completely agree, 100%. I've sat in a reading room. I shadowed attendings, I shadowed fellows, I shadowed residents. It really is an enlightening experience. And so I saw everything from, the car accident, patient hit by a car, polytrauma, all the way down to the PICC line nurse asking, is the PICC line in the right place? And it's a very, very hectic environment. And I think it's very important for the data scientists and machine learning scientists to understand this. And those developing the product need to know this. Disruptive change, that's another one. We're in California. The disruptive change is sort of the ethos. It's Silicon Valley, it's what you hear. And it's great, except when you're trying to sell to systems that are stodgy. You're selling to a hospital. Hospitals don't move fast. And they don't move fast for a reason, right? It's one thing if you're updating Microsoft Office, and maybe if you change the workflow and you slow someone down by 10%, they eventually get used to it. It's no big deal. It's another thing when you're updating a PACS or something else, and suddenly the clinician can't do their job. And now it's a matter of life and death, and there's a patient sitting there on that bed waiting for treatment, and the clinician just can't complete the next step because they don't have the information they need. And so it's a really, really big deal. And so because of this, you want to find the right product manager. If your target is a clinician, you want a clinician to serve as your voice of customer. As an engineer or a typical, a product manager from, say, Fitbit or anywhere else, so I worked at Fitbit, these folks don't know what goes on in a hospital, even though they're involved in maybe healthcare, tangentially or tech. They just don't understand the workflow of the processes, and if the person's going to serve as the voice of your customer, they need to have the background of the customer. And finally, targeting relevant metrics. And so you really need to make sure you're trying to solve the right problem. If you are trying to decide, should I biopsy or should I not? Deciding, is this actually cancer or not, isn't actually not the right metric, right? You want to have an algorithm that can tell you, should this be biopsied or not, which is a slightly different task. And so then once you're developing the solution, the question is, how good is good enough? What sort of sensitivity and specificity do you actually need? And I think it's a loaded question. You often run into situations where it's really easy to create that first solution, that paper, that first research paper, that you can present that first result to the clinician and generate some excitement. However, generating a level of reliability that's actually acceptable for clinical use on a day-to-day basis is really, really hard. It's the 80-20 rule. The first 80% is only 20% of the effort, but the last 20% is much, much more challenging. And the even more challenging part is as you're looking for more and more reliability, it gets even more challenging to get there. So if you really need that 99.99% accuracy, it's going to be really expensive, much more so than 99.9% accuracy. And one of the challenges there is that just achieving radiologist performance is likely insufficient. I don't know how many of you in the room, so earlier we were talking about self-driving cars and self-driving planes without a pilot on board. If I told you that the car would get in an accident just as often as humans, would you want to get in it? Probably not. If I told you it gets in an accident half as frequently as humans, would you want to get in it? Probably not. I mean, there is no below average driver, right? Just like there's no below average surgeon, there's no below average, lots of folks are very confident in their own abilities, it's always someone else. But at the end of the day, sometimes there are just folks who are gonna come at you from, driving in the wrong lane, come at you head on. Like, some things are unavoidable, but folks like the sense of control that they have. And so you need to beat radiologists by a significant percentage if you want to, really replace them in any way. And that's why I think it's unrealistic to assume that it's going to happen anytime soon. And so what is the solution here? I mean, I think there are lots of decision support tools that already exist. And so rather than trying to replace the radiologist, why don't you augment their workflow? They're used to using PACS now. It's been a decade or two. Why don't you provide other tools? Give them an advanced suite of tools that, instead of just sitting at a computer where they can scroll through images, have various buttons they can click that allow algorithms to run that say, highlight regions of interest, that prioritize the work list, whether it's an acute patient if, something is really serious, or if the hospital's at high occupancy, maybe you prioritize some of the likely normals. And so you can clear beds and open up space. And so at the end of the day, you can only really sell what you're allowed to sell. If you can't pass FDA clearance, you're not going to sell anything. And so decision support provides a much easier path to do this. You're not replacing the clinician, you're augmenting their ability. And if you're talking to engineers, like, this is a very standard neural network architecture known as a ResNet. You can speak to them in these terms and they'll understand it. And finally, I want to hurry up because I'm running out of time here. But at the end of the day, you need to find the right first customer. No one's going to solve this correctly the first time. And so your first customer is also a collaborator. And so you need to find someone who is culturally adaptive. They're willing to deal with the pains of new technology because everything's going to be flaky. Nothing's going to be perfect the first time. They also need to be open to collaboration because it's not going to be right the first time. They're going to need to help you because you're helping them, but at the same time, they need to be willing to help you. And then this is a new field for both folks, for both, the scientists like myself, but also the clinicians. And so you need to have an open dialogue. You need to have folks who are willing to learn in both directions. You need data scientists who are willing to go sit in the reading room and just sit there and watch clinicians work and willing to learn about medicine. We also need clinicians who are willing to learn the basics about machine learning, which I suspect a lot of you are because you're here. What is this algorithm doing? Why does it work the way it does? No one's going to expect the machine learning scientist or data scientist to perform clinical care, but also, and no one's going to expect the clinician to develop an algorithm. But at the same time, you need to speak the same language you can communicate. And finally, just one final plea. Set expectations appropriately when you're developing these solutions. There's a lot of hype in the space. And so I mentioned it came from RSNA. There were folks there advertising accuracy numbers that just not possible. And so they're doing either something wrong or they're being willfully dishonest. There's also folks just claiming performance levels that aren't achievable relative to radiologists, for instance. We recently, within the center, we tested 3 vendor-provided algorithms that said we can detect pulmonary nodules. There are lots of algorithms that do this now because there's an open data set. We found very, very wide variety in terms of performance. And I would argue, based on the numbers we saw, none of them were as good as clinicians. And so when you hear these claims of this algorithm is better than the radiologist, be careful as a clinician. View it with a bit of skepticism. And that's also a challenge, though, because you're not equipped to do that. That's not your job. You were never trained to validate algorithms. And so we need both sides to sort of come in with the right mentality. Clinicians should be skeptical, but also the product developers, there should be a little truth in advertising. And with that, I just want to thank you. And since I have the mic, I'm going to make one last pitch. So this is where I work for the Center for Clinical Data Science. We're at MGH in the Brigham, and we're hiring for a bunch of roles. And so if any of you fit into this, please reach out. I'd really appreciate it.
All right, fantastic session. How much time do we have for the Q&A? 5 minutes. 5 minutes, okay. Well, I'll get started. I think a lot of what we in this conference have focused on is this concept of precision medicine, but I think we want to get to a position where we're talking about precision health, where the former is reactive and the latter is proactive and preventative. So I'd like to hear your thoughts on opportunities for deep learning to move us from precision medicine to precision health. So who's want to
I
take
can
that?
kick it off. Hello? There we go.
Got it.
Yeah, I can kick it off. I think one of the biggest challenges is, in general, healthcare solutions tend to be extremely siloed. If you want data from the EHR, you go to a different place than if you want data from somewhere else. And a lot of these designing solutions for patient health rather than being reactive are going to require longitudinal studies. And so just acquiring the data to perform the analysis is extremely challenging because you're going to a million different databases and different vendor solutions, each of which have their own proprietary formats. Some of them may give you the data, some of them may not. They may just not want to give it to you at all. Others may want to charge you an arm and a leg just to access your own data. And so working this environment is extremely challenging. Even in radiology, where you have imaging and, say, the reports. In most hospitals, those are two different systems. At MGH, for instance, you're even looking at two different computers. The radiologist has two computers sitting next to each other, one for viewing the images, one for dictation. And so this siloing of data and this lack of interoperability is a real challenge. And I don't think there's a good way to push the vendors, at least right now, to work together.
All right, a question came in from the audience about empowering the patients to interpret the wearable data with AI. I think this is an interesting question, and it speaks to some of the things that several of you touched upon and some of the things that I mentioned in my brief introduction to the session, and that is opportunities to utilize our subjects, the patients that we're treating, to label or provide good examples for deep learning. What are your thoughts on that? How can we start to capitalize on that potential opportunity to move from precision medicine to precision health?
Yeah, let me take a shot at that, given some of the biases of my presentation. I definitely see the opportunity out here where empowering the patients way beyond they are right now perceived, which is much more on the passive, on the receiving side. And as we move into a patient-empowered delivery care system, where the patient will start taking decisions based on the information they are being provided. In fact, some of the feedback we are seeing already is the patient wants more information. That's the world we live in. So how we enable that, obviously there are some challenges, but one of the point which always keeps coming up is saying this overload of information, too much of information. Well, it's a matter of how do we visualize that. So in fact, the word which keeps coming back to me is, yes, there is deep learning, but there has to be the surface applicability of that, which is the UI part of it. How do we interact with the information? That is something we just need to work on.
So I also, before I joined the center, I worked at Fitbit, so I think I can answer this one a little bit as well. One of the challenges with wearable data in general is you get a ton of it. It's a fire hose. You can just get as much as you want, really. But the biggest challenge is that you don't have the ground truth label. You have all this data from day to day what the patient's doing, and you can infer to a certain extent, pretty accurately, how many steps they've taken, et cetera, their heart rate, you name it. But you don't know when an event occurred. You just know that you have this data. And so you have the day-to-day data sitting in your Fitbit, your Apple Watch, whatever. And you have, on the other hand, the ground truth healthcare data sitting in this hospital. And it's very challenging to merge the two because how is Fitbit going to get the hospital's data? How does the hospital know you're wearing a Fitbit? And how do you link the two and provide the data in a way that benefits both the company that is providing the data, but also the hospital and the patient? And so there's a lot of different stakeholders. It's hard to align incentives there.
Along the same line, I wonder whether we can begin to think of shifting our notion of control from a gold standard baseline that's population-based to the individual, so that your data from the day before and the weeks before become the controls. And if there's opportunities for us to manage the problem that you're describing, utilizing that flip in how we address control.
Yeah, I think there are opportunities. There's a long road ahead of us, and I think it's going to take time and willingness and buy-in from everyone. And it's just a matter of getting everyone in the right room. And I think events like these are a great start.
Okay.
Thank you, Dennis. Can we give a round of applause for our panel? We're a few minutes behind, and since we want to get everyone out on time for lunch, we'll take a 15 to 20-minute break. We'll come back at 10:45 for the abstract session. Thank you.